They can see you and hear. You can't see yours.
I want to see my face. Better. Oh, better. But they can see me.
You can start.
Hello, shall we start? Hello.
Yes, sir.
Yes, sir.
Hello. Okay. Good morning, everybody. I am Pranesh Char from formerly of Homi Center, Mumbai. Okay. So I will be doing problems, assorted problems from algebra, geometry, combinatorics, and number theory. So now you can look at the problem. You are able to see problem 9.
Yes, sir.
Okay.
Yes, sir.
Yes,
So
sir.
the problem, this is a very elementary problem. Let B, C be 2 points in the plane such that the length of the line segment BC is small a. Find the area of the region of all the points, that is the set of all points capital A, such that CA less than or equal to AB less than or equal to BC. So here B and C are two fixed points. A is a variable point satisfying these two inequalities. So what does it mean by saying CA less than or equal to AB and AB less than or equal to BC? Let's see. So this is the problem. Okay, now let K be the mid, we'll draw one perpendicular and one circle. Let K be the midpoint of BC. Draw the perpendicular bisector of BC through K, and since K is the midpoint. And also draw a circle with B as center and radius BC equal to A. Intersecting the circles at P and Q as shown. Okay, you are able to see this figure. Okay, we call the circle sigma. Now, what is meant by saying CA less than or equal to AB? CA less than or equal to AB with respect to the perpendicular bisector. See, if a point lies on the perpendicular bisector, then it will be equidistant from B and C. So if A lies on PQ, AB equals AC equals AB. If A lies to the left of the perpendicular bisector, what does it mean? It means that AB is less than AC. And if A lies to the right of the perpendicular bisector, it means AC is less than or equal to AB. Is that okay? Okay. So therefore, our point A should lie to the right of the perpendicular bisector. So that is what is meant by the first condition. So the first condition, CA less than or equal to AB, means A can lie anywhere, okay, towards this infinite line. So A can be lying anywhere in the infinite region. But what is meant by AB less than or equal to BC? A is at a smaller distance from B than from C. Then B is from C. Okay. So AB less than or equal to BC means you take a circle with B as center and BC as radius. Then whenever point A is in the circle, we see that AB is less than or equal to BC because the distance from A to the center B will be certainly less than or equal to the radius, and BC itself is the radius. So if you put these two conditions together, it means that A not only lies to the right of the perpendicular bisector, but also it is inside the circle. So that constrains the point A to lie in this bounded region, in this finite region, which is a minor segment of the circle with B as center and BC as radius. So what is the area of this minor segment? So how do you calculate the area of the minor segment, given that the radius is small a, and also given that given that K is the midpoint of BC. Okay, now let me go to the steps 2 and 3. So AFC less than or equal to AB means A is on the same side of PQ as C, and AB less than or equal to BC means A is inside the circle sigma. So therefore, there is a desired region is a minor segment of sigma with chord PQ as one of the boundary lines and arc PCQ as the other boundary line. So how does one find the area?
Sir, BK will be A by 2.
Sir, join BP and BQ.
Okay, join PB and
BQ.
BQ. Okay, fine. Very good. Then
Area of
Sir,
sector
then we can
minus
find
area
the
of
area of
rectangle.
triangle with PQ.
Sir,
We can find the length of PQ.
120 degrees. Sir, angle PBQ is equal to 120 degrees.
angle PBQ is equal to 120 degrees. That is correct because
Yes, sir.
see this since this is the perpendicular bisector, angle PBC PB will be equal to PC, and BC is also equal to BP. Therefore, this will be an equilateral triangle. PBC will be an equilateral triangle. Therefore, angle PBC will be 60. Similarly, angle QBC also will be 60. Therefore,
Its area would be pi a square by 3 minus root 3 a square by 4.
yeah, right. We're going to that step. Okay. So in the figure, the region is dotted. Now, since we have these 4 equal lines, all of which equal to A, we see that PBC and QBC are each equal to pi by 3, as you have pointed out. And then, hence, the area of the region will be the area of the sector minus the area of the triangle PBC. Now, pi by 3 a squared is the area of the sector. What is the reason? Reason is that it is 1/3 of the entire circle. Angle PBC is 120. Therefore, this is 1/3 of the, sorry, is that okay? Must it be 2 pi by 3 or pi by 3?
So pi by
Pi by 3.
Pi by 3.
Pi by 3, okay.
Sir, can I ask a question?
Just let me complete this step. And what is the area of the triangle PBC? What is the area of the triangle PBC?
Half base into height.
Triangle, sorry, not PBC, PBQ, because we have to subtract PBQ.
Half a square sine 120.
3 a square sine 120.
Yeah, half PB into PQ sine of 120, that will be root 3 a squared by 4. Actually, that will be the same as the area of the equilateral triangle PBC. Okay, so that will be pi by 3 minus root 3 by 4 a squared. Okay, so somebody has a doubt. What is it?
Yes, sir.
Yeah.
Sir, how did you know that we have to construct a circle here?
Well, see, that is motivated by the fact that AB is less than or equal to BC. Now, AB is less than or equal to BC. Therefore, A is at a shorter distance from B than C. So, so A is at, see, BA is less than or equal to BC. That means naturally, you know, the A should lie within this circle. That's the motivation.
So,
Yeah.
so why is it not 2 pi by 3 a square?
Well, that's my doubt. I think this should be 2 pi by 3. No? This is 120 degrees.
Yes, sir.
So this is incorrect. Please make it 2 pi by 3.
No, sir, area of circle divided by 3.
It's half theta into r square area of circle.
Half theta a square.
See, pi a squared is the area. Oh, this is right. Pi a squared is the area. 1/3 of the sector. 1/3 of the circle. So pi by 3.
Circle.
Yeah. So it's correct. So pi by 3 is correct. Well, I also get confused sometimes. So pi by 3 is correct because it is half r squared theta. That is the formula for the area. So it's pi by 3 is okay. Okay. So this is a very elementary problem because you have to simply locate the region for the first inequality and another region for the second inequality and take the intersection of these two regions. So the intersection happens to be a finite region. Now if you look at the upper half of the dotted region bounded by PK half chord, KC, this line segment KC, and arc PC, it has some significance. So comment, the upper half of the dotted region, suppose you call it gamma, bounded by the lines PK, KC, and arc PC, has some geometrical significance. Now what is that? If you take any triangle of any given shape is always written by its angles, then we can prove that there is a unique point A in gamma, that is in upper half of the dotted region, such that ABC is similar to T. So given any triangle T, there's a point here such that triangle ABC is similar to that triangle T. You can try to prove this. It's not difficult. For example, if the point A lies on anywhere on the boundary line PK, what sort of triangle will it give? It will give isosceles triangle, is it not? ABC, AB equals AC, because this is perpendicular bisector. Therefore, it will give isosceles triangle. Even if A lies on the arc PC, you will get isosceles triangle, ABC. Which two sides will be equal if A lies on the arc PC?
AB
and
BC.
A and BC.
Yeah, AB equals BC. So BA equals BC. So whenever point A lies on this boundary line or this boundary line, you will get isosceles triangle. But for this, the vertical angle will be less than 60. For this, the vertical angle will be more than 60. When I say more than 60, between 60 and 180. So as A goes from P to K, the angle at A increases from 60 to gradually to 180 minus. When this A lies on arc PC, the angle at B decreases from 60 to 0. So all isosceles triangles are covered by the boundary lines. Inside, there are acute angle triangles and the obtuse angle triangles. Non-isosceles triangles are covered. For example, how do you get right angle triangles? Which point say
when I go
We'll make a circle with BC as diameter and then we'll get
exactly. So BC as a diameter, you draw a semicircle. Okay, that semicircle will part of the semicircle will lie in this region. So any point in that on that arc, it will be half of this. It will be a quarter circle, I believe. Any point in that quarter circle will represent a rectangle. And if A lies below that semicircular arc, then it will represent obtuse angle triangles. And if A lies above the arc, it will represent acute angle triangles. So roughly, you will see that all sorts of triangles are represented by the points. You can prove it more strictly using using analysis. Okay. Yeah. So we'll go to the next problem. There is one thing you should note. When we say the area is the region is denoted by gamma, we include the interior, we include the line PK, and we include the RPC, but not KC. KC is excluded because if A lies on KC, it will be a degenerate triangle. So we are not interested in degenerate triangles. So that's the comment on this problem. So we go to the...
Sir, can we say the same for AKC?
Yes, QKC. You mean QKC?
No, sir, AKC. Sir, A being the variable one.
No, A is a variable point.
Yes, sir, that's what I'm saying, sir. And K would be fixed. So I'm saying can it be the same?
Oh,
for
you mean, no, well, no, ABC, it may not be true for AKC. Okay. It may not be true for AKC because some triangle shapes may be excluded.
Sir, how would we prove that?
See, if you take AKC, you are restricting yourself to, I mean, very few triangles. Right now, I cannot point
obtuse
to
angle triangle cannot be made at the least obtuse angle.
Somebody,
Obtuse angle triangle can't be made.
well, yes. Is it okay? Because, yeah, well, still,
Sir, they
maybe.
can be made, sir. If we
Sir, it
take
can be
AC
made.
as a diameter.
No, A is much closer to KC. Obtuse angle triangles will be there.
Yes, sir.
You can see, but
Yes, sir, there will be.
well, you have to. I mean, some angles will be certainly excluded. Maybe let me think and let us. Let's see. I mean, you can take it as an exercise yourselves. What offhand I cannot say, but you cannot. You can always take it as an exercise. If you restrict to AKC, then what sort of triangles are excluded?
Sir, for that, can we then assume that K was somehow B dash, and then again using the same theory, kind of, we will get all the points.
Well, it's one thing. Uniqueness, see, if, yes, sorry. Now I think I can clarify. If you take AKC, there may not be a unique point. There will be several points which represent the same triangle. That's possible, because I think we're in this bigger region for as far as K is concerned. So I believe you will have several, at least more than one triangle which represents the same triangle. See, only if you take ABC, every triangle is represented by unique point. But if you take the triangle AKC, then more than one point A can represent the same triangle. You get me?
Yes, sir.
So, okay. So you have to now take, you can now find out two positions of A for which AKC gives the same similar, AKC gives the same similar triangle. Okay. Right. Okay. We'll pass on to the next problem. Problem 10. There it has two parts. This is also an elementary problem. Let ABCD be an isosceles trapezium such that the lengths of the sides and the two diagonals form a two-element set AB. If A is greater than B, find A by B. So let's see what the problem means. So how many lengths are there totally when you take the isosceles trapezium and look at the sides and the diagonals? You have 6 lengths, 4 sides and 2 diagonals. So the lengths of all these 4 sides and 2 diagonals form a two-element set AB. This means each side is either A or B, and each diagonal is either A or B. But since the diagonals of an isosceles trapezium are equal, both will be either A or both will be B.
Sir,
Okay.
is the answer 1 root 2?
Yes, sir.
Root 2. Say isosceles trapezium is not a square. For the square, it is root 2 because square has also 2 lengths. And if you take length of the square, side length of square as 1, the diagonal is root 2. So A by B will be root 2. But for a trapezium, see, by a trapezium, I mean 2 sides are parallel and the other 2 sides are not parallel. We cannot take square as a trapezium.
So we can, so you are excluding the definition of trapezium, which includes square.
No. By definition, a trapezium, I mean, this I believe it's a standard.
Is the answer 2? Sir, is the answer 2?
Is the answer
Sir,
2?
is the answer 2?
Well, we'll find out.
Yes, sir. 2, sir.
2 is the
2?
answer. Well, it's not correct. 2 is not the answer.
Sir, is it the
Yes, sir,
golden
1 plus
ratio?
root 5 over
Root
2.
5 minus 1 by 2.
1 plus root 5 over 2.
1 plus root 5 over 2 seems to be correct. Okay. 1 plus root 5 over 2 is in fact correct. Okay. See, first of all, let us look. Let's fix the lengths. Now, since
Yes,
it's an isosceles trapezium, you see that these 2 base angles will be acute and these 2 angles will be obtuse. So, since this angle is obtuse, AC is greater than, so first of all, we describe the figure here. AB is parallel to CD. AB is the longer side, CD is the shorter side. AD equals BC. And since angle ADC is bigger than 90, AC is bigger than AD as well as AC is bigger than CD. So since there are only 2 distinct lengths, AC will be small a and The other two sides will be B each. Okay. AC will be small a, and AD and CD will be B each. Okay. Since the isosceles strip is, well, similarly, BD will be small a, BC will be small b, and AB is again is capital A. Why is AB capital A? AB is small a, because AB is bigger than CD. So once you have two distinct lengths, the bigger length will have to be A and the smaller length will have to be B. So we see that 3 lengths are small a and 3 lengths are small b. Okay, now we go to the application of Ptolemy's theorem. Every isosceles trapezium is a cyclic quadrilateral. The reason is that this angle, opposite angles add up to 180, just like these two adjacent angles also add up to 180. So by Ptolemy's theorem, we have a squared equals ab plus b squared, because sum of the products of opposite sides. So ab plus b squared is equal to a squared. So you see that this is a homogeneous equation a by b. You can divide by b squared, bring everything to the left hand side, and it becomes a quadratic equation a by b. And you get two roots, 1 plus root 5, sorry, it's 1 plus root 5 by 2. I think there is a small error. It's not root 3, it is 5, 1 plus root 5 by 2, because actually it's 2 cos 36. You are aware that cos 36 is root 5 plus 1 by 4?
Yes.
So the ratio will be root 5 plus 1. You can not necessarily use, if you don't know Ptolemy's theorem, I'm sure all of you must be knowing Ptolemy's theorem. Another, without Ptolemy's theorem also, we can solve this problem. You assume that you name one of the smaller angles as a small x. Suppose angle CAB is small x. Then you can find out all the other 7 corner angles in terms of x. How do you do that? See, since this angle is x, this angle will be x. And since this is an isosceles triangle, that is x, this will be x. And since this is x, this will be x. And this also will be x. So we have 2x here. And this is x here. And since AB equals AC, this also will be 2x. So 2x plus x is 180, because all these angles are angles of a triangle. Therefore, 5x is 180. Therefore, x is equal to 36 degrees. So this small angle becomes 36. This is 36. So this will be 3x, 108. And this will be again 72. Now you can apply sine rule for in any standard triangle, ABD, say. If you apply sine rule, so this is what I meant. So this proves that x is 36. Now one can use the sine rule to get a by b. How does one get a by b? A by sine a equals b by sine, a by sine of complete angle a is b by sine of this angle. So a by sine 72 will be b by sine 36. And if you look, find out a by b, it will be 2 cos 36. Is that clear? Yeah.
Can you show that Ptolemy's theorem proof?
Sorry, you can you? Can I?
The method of Ptolemy's theorem.
Ptolemy's theorem. What is the statement you mean?
No, sir, the method of solving.
Method of proving Ptolemy's theorem.
No, sir. In this question, how do we use
this question? Okay. What does Ptolemy's theorem state? It states that if ABCD is a general cyclic quadrilateral, then sum of the products of opposite sides, AB times CD, that is one product of opposite sides, plus the other product of opposite sides, AD times BC, equals product of the diagonals. That is Ptolemy's theorem. So AB times CD plus AD times BC equals AC times BD. But here we have A and B as the lengths. So product AB plus product B squared is equal to product A squared.
Okay, sir.
Okay. You take a pair of opposite sides, multiply by the lengths for both pairs of opposite sides. That will be, the sum will be equal to product of the diagonals.
So can we directly use theorem's results without proving it in exam?
Yeah, you can always. Okay. Ptolemy's theorem is a very standard theorem. Okay. That's your question. No? You can always use Ptolemy's theorem. Is that your question? Okay. Now there is a comment. Yeah. Right. Now note that this figure is actually part of the regular pentagon ADCBE. E is not there, with the triangle ABE removed. So if you draw a regular pentagon ADCBE and remove the lines EA and EB, you will get this parallelogram, this trapezium.
Sir, is it good to write our comments after the solution? Means what we feel about the question.
Is it good to where in the exam?
In the exam, like this was the comment that it's a regular pentagon or something different about the question that we feel.
But see, that's just a general addendum. So you don't have to. There is no. It doesn't fetch you any additional marks anyway. But
Sir,
if we have solved the question correctly, but our comment is wrong.
Your comment, actually, I can't answer the question because it doesn't matter, no? Whether you write the comment or not, it doesn't matter actually.
Okay, sir.
Okay, yeah. Okay. Now the exercise. Are there any other configurations of 4 points, like here A, B, C, D? These 4 points here form an isosceles trapezium. Are there any other 4 distinct sets of distinct 4 points, 4 distinct points A, B, C, D in the plane, giving rise to 2 distinct lengths? We have already seen one. The square is another example. Square also gives only 2 distinct lengths. So, as for example, ABCD is a square, or when ABC is an equilateral triangle and D is its center. See, the 4 points need not always form a quadrilateral. They can form a triangle with its a triangle also. The 4th point can lie inside the convex hull of the other 3 points. So you see that if ABC is equilateral triangle and D is its center, then also there are only 2 distinct lengths, because the sides of ABC are all equal. That is one length small a, and the distance from D to the vertices will be also equal, and that will be the smaller length B. So there A by B will be, for the triangle it will be 2 cos 30, that you can easily find out, and for the square it is a 2 cos 45, because this ratio is root 2, and 2 cos 45 is also root 2. Okay.
Sir,
but
50, 120 rhombus.
Sorry? Yeah.
Sir, a rhombus is 50, 120. 60,
Exactly.
120.
So the 60, 120 degree rhombus is another case. Their 5 lengths will be equal to one another, and the bigger diagonal will be A, because the bigger length is always represented by small a. So so therefore, I have written here the generalization. I mean, one more point. There are a few more cases in all of which A by B can be written as 2 cos alpha for some nice angle alpha. So, for example, you can find out alpha for a rhombus. What will be alpha for a rhombus?
$30 degrees only.
30 degrees again.
So depend on rhombus.
No, rhombus is, see, we need only 2 distinct lengths. It is a 60, 120 rhombus. Any other rhombus will have 3 distinct lengths. We don't want 3 or more. For 2 distinct lengths, the 60, 120 rhombus is the only one. Okay.
Sir, will there be a finite number of possible values of A by B, or we have found an infinite set?
There will be only finitely many cases. You can actually find out all of them, and in all these finitely many cases, A by B will be of 2 cos alpha. But the thing you see, the nice thing about this ratio is that it is greater than 1 because A is greater than B, but it's always less than 2, strictly less than 2, because 2 cos alpha is always strictly less than 2. So it's more than.
Is there a reason?
No, once you find out all the configurations, then you will see that all the ratios are of this form. Therefore, it has to be less than 2. we need to find out all the configurations. I think there are maybe, including the rhombus, there are 3 more. You can find out, you can try. That is left as a, an exercise.
Okay, sir.
Okay. Now, this is the other part of problem 10. All the points in the plane are colored using 3 colors. Prove that there exists a triangle with vertices having the same color such that it is either isosceles or its angles are a geometric progression. Okay, so when I say the plane is colored by 3 points, all the points in the plane are colored by 3 colors, we mean that there is a function from the set of points in the plane to a 3-color set. So each point is allotted a color. Have you come across any coloring problems like this? For example, if all the points on a line are colored by 2 colors, then there exists 3 points ABC on the line, such that AB equals BC and ABC have the same color.
No, sir.
The friendship theorem.
Yes, sir.
No,
Okay,
sir.
right. So there are several coloring problems. This is just one of them. You can there are coloring problems for line segments. There are coloring problems for points and so on. Now, how about this problem? So how do you solve this problem? There is an isosceles triangle with all the vertices of the same color, or there is a triangle with whose angles are geometric progression. So what is meant by geometric progression? If in a triangle, if the angles are in geometric progression, they have to be pi by 7, 2 pi by 7, and 4 pi by 7, right?
Yes, sir, because sum and product is constant.
Yeah, sum is pi, and if you take the ratio to be well, no, not necessarily. I think they can be. Sorry.
60 degrees.
We have only sorry. So we are going to make the angles this. I say they have to be pi by 7, 2 pi by 7, 4 pi is wrong. We are going to choose a triangle with these angles. I'm sorry about this condition. They need not be always these 3. Okay, we'll choose a triangle with these angles. Okay, which are in. This is just one set of angles. Okay. So this leads us to consider the vertices of a regular 7 gun, A, B, C, D, E, F, G. Okay. So let's take a regular 7 gun. So if you take a regular 7 gun, that is regular heptagon, look at the vertices. There are 7 vertices and they are colored by 3 colors. Therefore, can I say 3 of these vertices have the same color by pigeonhole principle?
Yes, sir.
Yes, sir.
So because if you divide 7 by 3, you get 2 as quotient and 1 as remainder. Therefore, at least 3 of these vertices must be having the same color. Okay, so now among those 3 vertices, suppose 2 are adjacent, A and B are adjacent, C. Then what are the possibilities for the third vertex? If you take the third vertex as C and it has the same color, then ABC will be isosceles. Is that okay? Because AB equals C. But instead, if you take ABD, then the angles of this triangle will be pi by 7, 2 pi by 7, and 4 pi by 7, because it's a heptagon. Okay, and if you take triangle ABE, that's also isosceles because AE equals BE, and you don't have to consider F and G because they are symmetric to D and C respectively. So it is enough to consider these 3 points. Okay, so if some 2 points are adjacent, we have either an isosceles triangle or a triangle with angles in GP. What is the other possibility? The other possibility is that no 2 are adjacent. If no 2 are adjacent, for example, we can take ACE. You see that AC is also isosceles because AC equals CE in this case. So this is an isosceles triangle. You don't have to take any other because if you take, for example, ACF, that also will be isosceles because AC equals AF. And all other cases will be will be similar. So if it, for example, if you take AD, then you have to take F because no 2 are adjacent. Then in that case, AF will be equal to FD. So you see that there is just one case here. AC is the only essential case. So there are essentially 2 cases here, and there are 3 subcases for adjacent points. So either you have an isosceles triangle or a triangle with the angles in GP. So I say once you think of a regular 7-sided polygon, then the problem becomes easy. Okay, is that okay?
Yes,
Sir, how
sir.
did we conclude that it is a 7-sided polygon?
Yeah, because when you have what is the number of points you have to take such that 3 of those points have the same color. What is the minimum number of points you have to consider such that 3 of those points have the same color?
7.
That's 7.
That's 7. So that's how we arrive at 7. Okay, we go to the next problem.
Sir?
Yeah?
Sir, how can we say that it was a regular 7 gone?
How
Sir,
can we what? You take a
Sir,
regular
it was
no, you take
Sir,
a regular heptagon and consider the vertices.
Sir, we took points in plane and colored them with 3 colors, sir. How can we say that it will always form a regular polygon?
No, all the vertices of a regular polygon need not have the same color. They will have different colors. Among them, you can choose 3 vertices which have the same color. See, 3 of the vertices among A, B, C, D, F, G. See, these vertices will have different colors, possibly. But
Sir,
3 of them must have the same color. That's the visual principle.
Okay, sir.
Okay.
So how do we conclude that in triangle ABD, the angles are in geometric progression?
ABD. Say you consider the circle here. So there is a circle passing through A, B, C, D, E, F, G. Okay. Each chord subtends at the center. Each side of the polygon subtends at the center 2 pi by 7. So AB subtends at D pi by 7. Okay. So this angle will be pi by 7. Now, if you look at angle DAB, that is the angle subtended by 2 chords, or you can say 2 arcs. So that will be 2 pi by 7. And the angle ABD, that is subtended by 4 arcs. So that will be 4 pi by 7. Okay, you are just using the standard theorem that angle at the circumference is half of the angle at the center. Okay.
Sir, why can't we use the angles pi by 13, 3 pi by 13, 9 pi by 13?
You can try that, but then you will have too many points. You have to take a 13-sided polygon. Then you will have too many cases, and you don't know whether there will be all the triangles will satisfy one of these 2 properties, isosceles or angles in GP. That may or may not be true. Perhaps I'm sure you will have 3 vertices which will neither form an isosceles triangle nor will be a triangle with angles in GP. That's a very large number. No? 13 is a very large number. Okay. So next problem. Okay. This kind of number theory, it has some combinatorial flavor. Prove that every positive integer n can be written as, this is the easy part, plus or minus 1, plus or minus 2, plus or minus 3, etc., plus or minus, etc., plus or minus k, for some suitable number k, and for some suitable choice of the plus sign and minus sign. You're at liberty to choose these signs, plus or minus sign, but you should be able to express every positive integer n in this form. Okay. Did you get the problem? Okay.
Yes, sir.
Okay. For example, how can you write 1? 1 is simply 1. 1 equals 1. Is that fine? Okay.
Yes, sir.
And how can you write 2?
1 minus 2 plus 3.
Minus 2 plus 3.
1 minus
2 plus 3. Okay.
We can write a number like this now. Minus 1
Yes,
plus 2
sir.
minus 3 all the way up to 2n.
Very good, very good. That's the correct answer. So, well, now I have written some numbers here. 1 equals 1, 2 equals 1 minus 2 plus 3, 3 equals 1 plus 2, and 4 equals 1 plus 2 minus 3 plus 4. But this method looks arbitrary and ad hoc. So we need to have a nice method. So as somebody pointed out, we look for a fixed number of consecutive integers, minimum number of fixed points, giving a fixed number. So for example, if you take a fixed number of consecutive integers, like k plus 1, k plus 2, will you get a fixed number with suitable choice of signs? In fact, 3 numbers are not required, just 2 numbers are enough. So this is what I mean by saying 2 fixed numbers are enough to get a fixed number. So 2 consecutive numbers are enough to get 1. So it is minus sign plus n plus 1. So n is prefixed by minus sign and n plus 1 is prefixed by plus sign. So you will always get 1. So we use this pair, such pairs to get 1s and add up to n. So that is 2 consecutive numbers are enough to get 1. Therefore, n equals minus 1 plus 2, that is 1 pair, that gives 1. Minus 3 plus 4, that gives another 1. Minus 5 plus 6, that gives another 1, and so on. And how long should you go? Until 2n, because this last pair also will give you 1. So there are n ones here, and you will get n. So it's an easy problem. But this has another part. Now, instead of first degree terms, you take second degree terms. Prove that every positive integer n can be written as plus or minus 1 squared, plus or minus 2 squared, etc. up to plus or minus squared, with suitable choice of signs plus and minus for some k. Of course, this k depends on the number n itself. So k is dependent on n. Okay. First of all, let's see how some numbers can be written. How can 1 be written?
1
only.
1
1
square.
is simply 1 squared. Is it okay? 1 is 1 squared. How can you write 2? Using the first few squares and any choice of signs. Can you take 1 and 2?
Minus 1, minus 4, minus 9 plus 16.
2
Yes,
squared.
please say that again.
The minus
Min-
1, minus 4, minus 1, minus 4, minus 9 plus 16.
Okay, so first 3 are minus signs and the fourth one is plus sign. Yes, you're right. So we have by trial and error, 1 is 1 squared. 2, as somebody pointed out, is minus 1 squared, minus 2 squared, minus 3 squared. See, 2 numbers are not, first 2 numbers are right because the sum is odd. Whatever combination you take, it will be odd number. But if you take 3 squared, 1 squared, 2 squared, 3 squared, 3 squared is too large when compared to 1 squared and 2 squared. Therefore, you won't get 2 again. But if you take 4 squared, now you want to subtract the first 3 squares, you will get 2. How about 3?
2 square minus 1 square plus 2 square.
Exactly, minus 1 square plus 2 squared. Now, how about 4?
2 square.
So minus 1, minus 4, minus 9, minus 16.
Minus 1, minus 2, minus 3. A plus 3.
Okay, minus 1,
minus
minus 2 squared plus 3 squared. Or if you observe that, if you change the sign here, what do you get? Plus 1 squared. So you will add, you'll be adding 2. Therefore, you get, you can, both answers are okay. Either you can take either minus 1 squared, minus 2 squared, plus 3 squared, or this. Okay. Now, again, we look for a fixed number of consecutive squares, which give a fixed number for a suitable choice of signs. So will n squared and n plus 1 whole squared give a fixed number?
Sir, I have just found that k square means minus k square plus k plus 1 square plus k plus 2 square minus k plus 3 square gives a constant number 4.
Please say that again. What is the order of signs? Just give me the order of signs.
Order of, sir, I didn't understand.
Order of plus and minus sign. So you just say plus, minus, plus, plus, minus, or plus, minus.
Okay, minus, plus, plus, minus. Yes, sir.
Minus, plus, plus, minus will give a negative number.
Yes, sir. Minus 4.
Minus 4. So we want a positive number. So
sir, plus, minus, minus, plus.
Exactly. So plus, minus, minus, plus.
Sir, and then we'll reduce it to mod 4.
Yes, exactly. So
and
by
we'll use induction.
Yes, very good, very good. So n squared minus n plus n whole squared minus n plus 2 whole squared. This should be plus actually. Sorry, it's it should be plus n plus 3 whole squared equals 4. Because then n squared terms will cancel with the other n squared terms. And you see that 6n minus 6n will be 0. And you have minus 1 squared minus 2 squared plus 3 squared, which is 4. Okay. Now these 4 equations above and 1 will help us to solve the problem. So already somebody has found out. So how does it help solve the problem? You use the 1 equal to 1 squared to get the next number 5 and next number 9, etc. 1, 5, 9, 13 in arithmetic progression. So how do you get 5? 1 squared is 1, and the next 4 numbers will give you 4 because these are 4 consecutive squares with plus, minus, minus, plus sign. So this will give 4. So 1 plus 4 is 5. And how do you get 9? Add 4 more numbers with the same combination, and that will give you another 4. So 1 plus 4 plus 4. That will give you 9. And how do you get 13?
So we'll add 4 more numbers.
10, 11, 12, 13.
10, 11, 12, 13, and so on. Okay. Now we have 2 equals minus 1 square, etc. Now to this you will go on adding 4, you will get 6, 10, 14, etc. For example, 6 will be equal to these 4 numbers, which give you 2, plus 5 squared minus 6 squared minus 7 squared plus 8. So this will give you 4. So 2 plus 4 is 6, and so on. Since 3 is minus 1 squared plus 2 squared, we can express multiples of 4 added to 3. That is 7, 11, 15, etc. In terms of the squares. So for example, 7 will be this 3, this is 3, plus 4. 3 squared minus 4 squared, etc. This will give you 4. So 3 plus 4 is 7. And finally, since 4 is this combination, you will get 8, 12, 16, etc. by the same combination, because 4 and 4 is given by the same combination. So this will be 8, and so on. So do all these 4 arithmetic progressions cover all the, do they all cover the natural numbers? Yes, because you have all the numbers 1 mod 4 here, all the numbers 2 mod 4 here, and all the numbers 3 mod 4 here, and all the numbers 0 mod 4 here. So all the natural numbers are covered. So hence every positive integer can be expressed in the desired form. So these 4 collections of numbers cover all the natural numbers. Now there are some.
Sir, can you show the previous slide?
Sorry, previous one, yeah.
Can you please show the previous? Yes, sir.
The previous slide. This one? Which one do you want?
Done.
This one. So this is not minus sign, this is plus sign.
Yes.
Is it okay? Okay.
So can we say that we can do this for every single integer except 0?
0 also is, okay. why every integer, every negative integer also can be covered now, because you just change the signs, and 0 also can be covered. How can you cover 0? It's easy. You just write plus 4 and minus
4 minus 4.
Plus 4 minus 4.
Plus 4 minus 4 gives you 0. See, somebody already gave the expression for minus 4. We changed the signs to get plus 4. So how many squares will be required to get 0 then?
8.
8 consecutive
Plus,
squares.
minus, minus, plus, minus, plus, plus, minus.
Exactly. You're right. So a corresponding exercise will be there. So prove that in each case, there is not just one way, but there are infinitely many ways of expressing each integer in the desired way. You have just given the solution for this also. Just
Adding 0.
Go on
Plus
adding
4
zeros.
minus 4.
And the zeros can be obtained by using how many integers? 8 integers.
8, 16.
Right. So go on adding 8 integers, 16 integers, and so on. So you see that every integer can be obtained in this way in infinitely many ways. So it's true for first degree as well as second degree. For first degree, how many numbers are required to get a 0?
2. 4. 4.
No, 4. Because 2 will give you 1, and the next 2 will give you -1, say. So 1 minus 1, 0. So for 1, for first degree, it's just 4 numbers. For second degree, it is 8 numbers. Now the question is, how many fixed number of cubes, consecutive cubes will be required? Suppose we want to go 1 degree higher, that are required to get a fixed number.
8.
8. So you're right. And what will be the fixed number? Well, you have to calculate anyway. This is just exercise. It's homework. So you just try to calculate.
I think it would be plus plus minus 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 plus plus.
Yes, you are right. So you have to just simplify and find out. You can take the first 8 cubes. You don't have to take n cubed, etc. N plus 1. You can take 1 cubed minus 2 cubed, etc. Okay. That will be a fixed number. Okay. But will our statement be true for
how did we get any idea that 8 cubes will work?
Well, see, 4 cubes, 4 squares have worked for 0 for the squares, 4 consecutive, and 2 numbers for this first degree. So you make a guess, 2, 4, and this will be 8.
It may be 6.
It could be 6, but then with 6 you won't be able to get. Okay, it could be 6.
Good guess.
Yeah, you have to guess only. But there is another way to get. There is another way to say that 8 cubes will do, because
the number 432.
Let me complete. 4 consecutive cubes will give you a linear equation in T. So the next 4 consecutive cubes will give you a linear equation in T with change. Suppose you change the signs, so the T coefficient will get cancelled, and you will get a constant term. That's the idea.
This is the number 432.
That's too large a number. I thought it will
32.
be
108.
48. It will be
108.
Sorry?
108, I guess.
No, 48. You will get 40. As far as I remember, it is 48. That you can find out yourselves. Okay, we go to the next problem. In an isosceles triangle, AB equals AC, and the vertical angle A is 20 degrees. So this means the other two angles are 80 degrees each. It's a very standard problem, but it's a nice problem. D and E are points on the equal sides AC and AB, such that angle DBC is 60 degrees and angle BCE is 50 degrees. Prove that angle BDE is 30 degrees. So first we draw the figure. Yeah. So
yes, so it's a very well-known problem.
It's a very well-known problem. Very good. Should I skip the problem then?
Yes, sir.
Yes, sir.
Yes, sir.
No, sir. No, please don't.
Well, sir, in this problem, we have to only do the construction and making isolation.
Sir, that 40-20-20 construction means 40. Yes, sir. 20-40-20.
There are several geometric proofs. This is one of my geometric proofs. So what you do is, so first of all, let me explain the hypothesis. So ABC is an isosceles triangle, AB equals EC. D is a point such that DBC is 60 and E is a point on EB such that ECB is 50 degrees. And you have to prove that angle BDE is 30 degrees. This angle is 30 degrees. The construction is, you symmetrize the figure. Okay. First of all, you observe that angle BEC is 50 degrees. And therefore, BEC is an isosceles triangle, B equals BC. Okay. Now we symmetrize the figure by drawing DF parallel to BC. So you get an isosceles trapezium DFBC, and we join CF and let O be the intersection point of the diagonals BD and CF. So we see that BCDF is an isosceles trapezoid, and triangles BOC and DY for equilateral triangles, because this angle is 60. Okay, I'll quickly go through the proof. Therefore, BO equals BC, because this is an isosceles. But BC is already equal to BE. Therefore, we see that BE equals BO equals BC. Therefore, BEC BEC equals, BEC is an isosceles triangle. Therefore, angle BEO. BEOE is an isosceles triangle. Therefore, this is 80 and this is 80. And therefore, angle EDF will be 180 minus 80 plus 60, which is 40. So this angle is 40. Also in the triangle BFC, this angle is 40 because this is 80 and this is 60. So that's 40. So this 40 and this 40 will make this triangle isosceles. So EO equals EF. But DF and DO are already equal. Therefore, this becomes a kite. DFEO becomes a kite. Therefore, DE bisects the angle FDO, but FDO is 60 degrees. Therefore, this angle will be 30 degrees. That's the proof of this particular geometrical proof. This is one of the geometrical proofs. There are several geometrical proofs. You can use trigonometric proof also. You can,
Sir, using sine rule.
Oh, exactly. I have given the brief description here. So use the sine rule for two triangles. You will get some equation like this. Here, actually, BD equals BD and B are again expressed in terms of BC. Therefore, BC will get cancelled. You will get a nice equation in theta, and solve for theta, and you will get theta equal to 30 degrees. So anyway, this will be sent to you by email, so don't have to worry. Okay, we go to the next problem. This is just a variation of one of the previous INMO problems. If Fn denotes the number of integer-sided triangles with perimeter n, then prove that F2023 is greater than F2020 and F2021 equals F2024. What does it mean? The number of triangles with the 2023 as perimeter is greater than the number of triangles with the perimeter 2020. Of course, this you may expect because this perimeter is bigger, but all the sides should be integer-sided triangles. But surprisingly, F2021 will be same as F2024, even though 2024 is bigger than 2021.
Sir, so I think we will get some sort of recurrence relation.
Well, recurrence relation, I think that will be complicated.
Sir, ABC will be the sides, and then A plus 1, B plus 1, C plus 1 will also be the sides.
Exactly. See, look at the difference. The difference is 3. So this suggests that if you take any triangle with perimeter 2020, and add 1 to each side, you will get a triangle with 2023. And triangle inequality will also be satisfied. Similarly, that will be the case here. But what is the difference between these two? You should get at least one more triangle with perimeter 2023, which cannot be obtained by adding one of this type. Okay, but here for each triangle with perimeter 2021 or rather with perimeter 2024, there will be a corresponding triangle with the 2021. So here some kind of bisection has to be proved. Here there will be a
triangle with sides. Sir, a triangle with sides 1, 0, 1, 1, 1, 0, 1, 1, and 1 will do the job.
Sir, 3k plus 2 and 3k plus 1 will be their form. So directly we can't reduce them to like 4, the perimeter 4, 1 with triangle 4 and that like that.
Well, you're talking about the recurrence relation.
Yes.
Okay,
sir.
let me complete my proof. So let ABC be the sides of a triangle with A plus B plus C is equal to 2020. Then as somebody pointed out, A plus 1, B plus 1, call it X, Y, Z. That also forms the sides of a triangle because X plus Y is greater than Z because A plus B is greater than C. So sum of these two sides will be greater than third side and so on. Therefore, for each triangle with perimeter 2020, there is a different triangle with perimeter 2023. But there is at least one triangle. So this map, ABC going to A plus 1, B plus 1, C plus 1 is a 1-1 map. But it's not an onto map because you can always find a triangle with 2023 as perimeter, that cannot be obtained by adding 1 to each of ABC. Can you specifically point out at least one triangle?
Yes, sir. 1011, 1011, and 1.
Oh, that's what you said. Okay, you
So
are right.
it has one of the side of 1.
One of the sides has 1. 2023 will allow one of the sides as 1 because the other two can be taken as equal. So if at all you want to get it from ABC, then the ABC values must be 1 0 1 0 1 0 0 and 0. This is not possible. Okay, so this is one example. Do you think there will be other examples also?
Yes, sir. There should be where triangle inequality is not followed.
No, sir, this
So
will be the
detect a
only
number
example.
from first two and add twice in it. तो कोई भी एक नंबर को पहले दो में से माइनस करके तीसरे में ऐड कर दिए.
Okay.
Sir, this will be the only case.
Huh?
Sir, this will be the only case, and there will be another for 2020.
No. See, if you take, for example, 3 here, you take 3 here and manipulate these two sides so that when you subtract 1,
1 0 1 0.
Sir, but for 2020, we will also get a triangle.
No, you have to. No, there the triangle inequality should not be satisfied. So these two will be unequal there. See, you could take 3 here, but
Yes,
these two has unequal sides. Don't take equal sides here. See, if you take 3 here, the sum of the other two sides will be 20 20. Okay. So you take, for example, 1 0.
Sir, 1 0 1 1.
1 0
1 1.
Other one?
Sir, and the rest two numbers will be different, means anything.
No, not
just the
any,
perimeter should be satisfied.
Two particular different numbers, not any any different numbers. You have to take them very close also. So what are the closest?
1 0 1 0.
1009 and 1011.
1009, 11 and 1009 same. So that will be 3 here. Okay. Now you subtract 1 each. What do you get? You get 1 0.
Triangle inequality is not satisfied.
Not satisfied. So for 3 also you will get a triangle. Maybe for 5 also you will get a triangle. Once you take them very close to each other.
So
okay?
if you take 1 0 1 1 and the remaining two side may be A and the perimeter minus 1 0 1 1 minus A, means 1 0 1 2 minus A.
Yeah, possible. Yeah, that could be the
It's a complete family of the solutions which will not satisfy.
Exactly. Yes, you're right. Okay. So there will be many more triangles. That's what I just wanted to say. Okay. Yeah. Okay. So now let's go to the next. So since we found out one triangle, this itself is enough to prove that 2023 is greater than 2020. Okay, we go to the next part. This was my question. So we have already answered that. Okay. Now we prove the equality here. Okay, we argue as before to say that there are at least as many triangles with the perimeter 2024 as there are with the perimeter 2021, because if you take a triangle with perimeter 2021 and add 1 to each, you will get a triangle with perimeter 2024. Now, conversely, if you take a triangle with perimeter 2024, you should always prove that x minus 1, y minus 1, z minus 1 also forms a triangle. So how do you do this? So you have to prove that the triangle inequality is in fact satisfied here.
Sir, by contradiction.
Okay, let's see. The contradiction is obtained in a very particular way. So all we need to prove that here is that, for example, a plus b greater than c. Now, since x plus y is greater than z, because that's for 2024, if you replace x, y, z by a plus 1, b plus 1, c plus 1, you get a plus b is greater than c minus 1. So what we need to prove is a plus b is greater than c. But at least we have a plus b greater than c minus 1. So does it follow that a plus b is greater than or equal to c?
Yes. Yes,
because
sir.
they are integers. A, b, c are integers, therefore it will follow that a plus b is greater than or equal to c. Only you have to prove that equality does not hold here. Okay. So how does one prove equality does not hold good here?
Sir, a plus b plus c.
Assume equality.
Therefore, that they will not be integer by.
The sum is odd, so it cannot hold.
Okay, let's see. If a plus b equals c, then x minus 1 plus y minus 1 equals z minus 1. That means x plus y equals z plus 1. Add z to both sides, you get x plus y plus z is equal to z plus 1. Do you see this is a contradiction? Because x plus y plus z is 20, 24, and right hand side is 2z plus 1. So where is the contradiction?
Even and odd.
Yes,
Even
2z
and odd.
plus 1 is odd, whereas 20, 24 is even. So this cannot happen. Therefore, a plus b cannot be equal to c. Therefore, you see that the map is actually 1, 1. Therefore, the number of triangles with perimeter 20, 21 and with perimeter 24 will be equal. So why do you think, although the difference is 3 here and the difference is 3 here again, one is inequality and the other is equality?
Sir, because in the first 2023 is odd, in the second 2024 is even.
Exactly. So
A smaller
if the greater number is odd, you will have more triangles. But if the greater number is even, you will have equal number of triangles, even if you add 3. This can be proved in general. Okay. So these are just 2 pairs of numbers with difference 3. In fact, there is a general formula for f of n. We could use that also, but we don't need the formula because that itself is obtained with some effort. So without using the formula, we are able to prove these inequalities. Okay, right. The medians of a triangle, divide it into 6 smaller triangles of equal area. This is a very trivial result. Okay. There's 2 parts. The medians of a triangle, divide.
It can be proven by the midpoint theorem and properties.
Sir, the first part is obvious, means.
Yes, exactly. That's why I'm not going to prove it. So the medians of a triangle divided into 6. So the medians of a triangle concur at centroid G. We know that each median bisects the area. So even this in this triangle also, this is the median. So the area is bisected. So using the fact that these 2 areas are equal, these 2 areas are equal, and these 2 areas are equal, and the sum of these 3 is equal to the sum of these 3, one can easily prove that all the 6 areas are equal. So I'm not going to say anything more. Let's go to the next part. Let P be a point.
Just the reverse.
Just the reverse, yes. Let P be a point. Oh, you want me to go back?
I was just saying that just the reverse system, you can add the areas and get 1:1 ratio.
Yes, you mean for part A? For this part?
So we will have to do, I think, casework here.
You will have to?
Casework.
Guesswork. Okay, no cases. Here you mean? For part A?
No, sir, in the next question, where any 3 of the areas are given equal.
Okay, so we go to part B first. So we are here. So let P be a point inside a triangle ABC such that AP, BP, CP meet the opposite sides in DEF respectively. Prove that if any 3 of these 6 areas are equal, then P is the center of this triangle. Okay. In order to answer this, we are looking at the converse part. So in how many ways can we choose 3 areas in essentially different areas, different ways? So we make a list. So there are 4 different ways you can choose 3 areas. Here you see that these 3 are adjacent. All the equal areas are denoted by X. So all these 3 areas are equal. And the other 3 areas are denoted by UVW. So this is one way. Even if you take here, it is same as this. Whether you take here or here, it is same because it's on one side of the median. All the 3 are one side of the median. Now, the other way is 2 adjacent and 1 slightly remote. So these 2 adjacent, that is remote. But there is another way also. These 2 adjacent and that is slightly remote. If these 2 adjacent and these 2 adjacent are different because these 2 adjacent are on a side, these 2 adjacent are with respect to an angle. So these 2 are essentially different. And the 4th way is to have all the 3 alternate, X, X, X. Is that okay? So there are 4 ways in which you can choose 3 equal areas. In all these 3 cases, you have to show that all these 6 areas are equal. U is equal to V is equal to W is equal to X, which means that P is the center of the triangle. Okay. So let's go to part 1. Even before we go to part 2, let's make a general observation. If you have any median, any point P like this, area PBD by area PCD is BD by DC, because they are the areas standing on these different bases but same height. And BD by DC is also equal to ABD by ACD. And do you say why all these three fractions are equal to this APB by APC?
By subtracting equal area?
Sir, if A by B equal to
In
C by
ratio.
D, then A minus C upon B minus D is also equal.
You subtract numerator from numerator and denominator from denominator, you get these two. So we will use this this particular idea. Okay. So we shall prove in each case that U is equal to V is equal to W, which gives us the conclusion. Okay. Now, okay, for the first part, okay, here x by x equals V plus W by U plus X, and x by U equals X plus X by V plus W, and so the third side, V by W equals U plus X by X plus X. Now using these three, you can easily prove that U is equal to V is equal to W. Okay?
Yes, sir.
It's a very easy. And part 2 is also very similar to 1. Okay, so
isn't there any way of doing without casework? Means we'll have to do 4 cases separately.
Of course, you have to do 4 cases separately. 3 of them are easy. 4th one offers very slight difficulty. That's all. All the 4 cases are easy, in fact.
No, sir, cases are easy, but I was asking that problem was looking so.
I don't know any other way of doing it. Without, see, how will you prove? See, you have to take 3 equal areas and other equal areas. So you have to first choose, no? So there will have to be cases.
So, but the question was designed in a way. So the question maker won't be knowing the case works. He would have thought something, means some thought would have come.
The proposer would not know the cases?
So the proposer would know the cases, but he won't do cases to check if his proposition was true. He would have done something different and then he would have got a result which he proposed the question.
No, you would have thought of, see, if all the 6 areas are equal, then definitely the triangle is, then P is the centroid. Then he would look at fewer number of areas, 4, 5, 4, 3. Then he would do it for 3, but for 3, he would look at different cases. Proposer would have looked at different cases and would have concluded that in each case P is the centroid, and that's why he proposed the problem. I don't think he would have, just like that, he would, without looking at the cases, he would have proposed. I mean, this is my opinion. Okay, let's keep the opinion to ourselves. Let's proceed.
Okay, sir.
Okay. This is anyway personal opinions. Okay, this is exactly similar to 1. So we look at the third part. Again, 2 adjacent, 1 remote. Again, you look at. I think you will get 3 pairs of equal fractions. You have to just. Well, this is my method of obtaining U equal to V equal to W equal to X. If you multiply all the 3, you get W X equal to UV, and you use this again in 1 or 2 cases, the next 2 fractions, to get W equal to U, and then U is equal to X, and then conclude that U is equal to V is equal to W is equal to X. This also will be easy. But look at the last case. Finally, if you have alternate things, you have cyclically changed fractions. So X by U equals W by X plus by V plus X. Then you cyclically change UVW, you'll get the other 2 fractions. X by V equals this is X by V equals U plus X by W plus X, and X by W equals V plus X by U plus X. So how do you think you would solve this problem? You would prove the equality of UVWX.
Multiply.
If you multiply, what will you get? You will get right hand side product will be 1. Therefore, you will get X cubed is equal to UVW.
Yes, sir.
X cubed is equal to UV. Will that help?
I will bring x by u and then eliminate it in the first equation.
Substitute w by w plus x equal to t1, u plus x equal to t2, v plus x equal to t3 to simplify the denominators.
To simplify the denominators? Well, you are bringing in more variables.
So x
But
cube.
we can look at 2 at a time.
Okay.
X cube equals to UVW. So x by u we will get in terms of w and v. We will substitute in the first equation. So we will be eliminating u.
Okay. Then okay.
Sir, can we make each of the equation quadratic in X?
Yes, each is a quadratic in X. Yes.
So we subtract the two quadratic equation, and then we can get the equality of X with U and V, any one of them.
Okay. Well, will you get equality? No, you will get X in terms of UVW. No, linear equation X, because X square term gets cancelled. You will get a linear equation X UVW. So X can be expressed in terms of UVW. Yeah. In fact, if you multiply all the three, X cubed is equals UVW. So use that and perhaps and manipulate somehow. You will, I think you will be able to get it. Okay. But have just a slightly different method. Suppose two of UVW are equal. Say U equals V. Without loss of generator, you can assume that U equals V. Then see what happens. Then 3 gives W equal to X. Then 1 gives X by U equals 2X by U plus X because W equals X. So this itself will give you U equal to X. And then therefore you have U equal to V equal to W equal to X. So if any two of these are equal, then immediately it follows that U equals W equals X. What is the opposite thing? No two are equal. If no two are equal, then I think we'll consider two cases. First case is U less than V less than W. Then the equations 1, 2, 3 will respectively give U less than X, X less than V, W less than X. Let's see why. Okay. See, if U is less than V, from the last equation, this denominator will be less than this denominator. Therefore, W is less than X. Now, U is less than W also. Therefore, you will get X less than V. Now, V less than W. Therefore, you get U less than X. So that's what I have written here. So you get U less than X, X less than V, W less than X. So if you look at the second and third inequalities, you have W less than X, X less than V. Therefore, W is less than V, but that's a contradiction because we are assuming that V is less than W. But here we get W less than V, so that's a contradiction. So U less than V less than W is not possible. What is the other case? Since we have a cyclic arrangement, the other case would be U less than W less than V. And again, from 1, 2, 3, you get X less than U, X less than V, W less than X. Again, if you look at first and third, W less than X, X less than U will give you W less than U. But that contradicts W greater than U because U is less than W here. Here, W is less than U. Again, a contradiction. Therefore, and these two cases are enough. Therefore, it cannot happen that all the three are distinct. So if it cannot happen that all the three are distinct, two of them will have to be equal, but equality of two of them will imply the equality of all these quantities. So that's why all the four quantities are equal. So you don't have to do much calculation here. Just assume some inequalities, and then using inequalities, you can prove this, get a contradiction and prove these things. Is that okay?
Yes, sir.
Yes, sir.
So sometimes it's easier to work with inequalities rather than equalities. That's the idea in this problem. Okay. So we have proved in all the four cases P is a centroid. Okay. I think I have enough time to work at least two more problems quickly. Find the minimum value of root of x squared minus 2x plus 10 plus root of x squared minus 6x plus 89 as x varies over all the real numbers. So is it a calculus problem or a non-calculus problem?
Sir, non-calculus, because INMOD never says you need calculus.
Okay, that's a good guess. Anyway, so we'll do it without using calculus. But first of all, what do you think we are going to use? Algebra, geometry, trigonometry?
We can use
Sir, we can use algebra.
Coordinate geometry.
Well, let's see. Let's see. Well, coordinate geometry include and some geometry. So what is the guarantee that, first of all, for all real x, this is a well-defined square root?
Because we can.
It's always positive. You can convert it to perfect square.
The x minus 1 whole square
less than
is
0.
9. So the least value is 9. Therefore, it is always positive. Here it's x minus 4 whole squared plus
x minus 8 whole square plus 25.
Minus 8 whole squared, you're right, plus 25. So that's also positive. Therefore, for all real x, the inside quantities are positive. Therefore, this is a well-defined quantity. Now, this is our, we solve the problem without using calculus. Let q of x equal to the sum, given sum. We would like to interpret each of these two terms as a distance between 2 points. What is, first of all, q of x? It is, the first term is root of x minus 1 whole square plus 3 minus 0 whole square, because that is 9. Second term is x minus 8 whole square plus 5 minus 0 whole square. So the first term is the distance between, you can say, x3 and 1, 0. This is the distance between x5 and 8, 0. But, we need a common point here. So it looks as though there is no common point here. So we just interchange the 3 and 0 and 0 and 5. So we rewrite it as, instead of 3 minus 0, we rewrite it as 0 minus 3 and 0 minus 5. Now you see that there is a common point. The first term is a distance between x0 and 8, 5. Sorry, 1, 3. Well, between the pairs, let me look at the, so the first term is the distance between x0 and 1, 3. The second one is between x0 and 8, 5. So what is the common point here? X0 is the common point. So now we plot it in the coordinate plane. So the first term is the distance between 1, 3 and x0. The second term is the distance between 8, 5 and 3, x0. Is it okay? There may be some, okay, this is okay, I think. Here,
sir, are you going to apply that reflection process?
Exactly. So we wish to minimize q of x, which is ax plus xb, as x varies on the x-axis. So now the problem reduces to this geometric aspect, as x varies on the x-axis, for which point x, ax plus xb will be minimum. So as somebody pointed out, we reflect the point A. You can reflect the point B also. Here we reflect the point A. So let the reflection be a dash, which is minus 1 comma minus 3. And you join a dash and b to intersect the x-axis at P. So now we will prove that AP plus PB is the minimum of all values of AX plus XB. How do you prove that? Since now you see that x-axis is the perpendicular bisector of A dash, because A dash is the reflection. So any point on the x-axis will be equidistant from A and A dash. Therefore, AP plus PB will be equal to A dash P plus PB, but that's a straight line. Therefore, it is A dash B. But by triangle inequality, A dash B is less than A dash X plus XB. But A dash X is AX. Therefore, A dash X plus XB is equal to AX plus XB. So effectively, what is happening? We have proved that AP plus PB is less than AX plus XB by using very elementary geometry. So we see that P is the required point, and all that we need to do is this is what is happening. So AP plus PB is AX plus, so as long as X is different from P, and therefore AP plus PB is minimum, and this minimum value is given by A dash B. But A dash B, A dash and B are known points now, 1 and minus 3 and 8, 5. So the distance is root 130. You can also find out the point P because you know the equation to the straight line, and put y equal to 0 and you will get the x coordinate of P, which I think will be 29 by 8. Okay. So it's just convert the this algebra sum or whatever, calculus sum into a coordinate geometry problem. Okay. We use the reflection principle. This is also a very standard point. One comment is that if you look at all possible ellipses with A and B as foci, the one that touches the x-axis, the ellipse that touches the x-axis will touch the x-axis at the same point. So there is some interpretation like that also. If you look at all the ellipses, okay, with A and B as foci, some of them will not touch the x-axis at all. Some of them will intersect the x-axis at 2 points. There will be only one which touches the x-axis at P, and that will be the same point P here. Okay, we go to the next problem and finish it quickly. Okay, there are 11 positive integers having the property that if any one of them is deleted, the remaining 10 can be divided into 2 subcollections of 5 each, because 10 numbers will remain. So they can be divided into 2 collections of 5 each with equal sums. Prove that all the 11 integers are equal. Just understand the so there are you can delete any positive integer, and the remaining 10 integers can be divided into collections. It's like a weighing problem. Suppose there are 11 weights with positive integral weights. If you delete any one of the weights, the remaining 10 weights can be balanced in a balance with 2 pans. You keep 5 weights on one pan and the remaining 5 weights on each pan, and then they will balance. So you can choose always 5 suitable weights on one pan and the remaining 5 on the other pan, so that they balance each other. Prove that all the weights are equal. Is the problem understood?
Yes, sir.
Yes, sir.
Okay. So it looks like a very kind of inaccessible problem, but still we have to look at some properties of these. Suppose you call this property, say, P. Let the given property called P. Then this P property P will be unaltered if you add the same number K to each of them. Suppose A1, A2, etc., A11 are the integers. Then A1 plus K, A2 plus K, etc., A11 plus K will also satisfy the property P.
Sir, are we looking at the base case? Means trying to look at the base case?
No, not the base case. We are looking
with
at some
one number being 1 and the one number.
No, not really. Not right now. Not really now. See, first we look at the possibilities of the property P remaining the same if some changes are made to A1, A2, etc., A11. So let me repeat: A1 plus K. If you add the same integer K to each of these numbers, the property is still retained. Even if you multiply by a non-zero constant K, positive or negative doesn't matter, the property P is still retained. Okay, because you have Ka1, Ka2, etc., Ka11. Since the A's property satisfies the property P, the Ka's also satisfy the same property P. So is this or these 2 points understood? Addition of K and multiplication. Okay.
Yes, sir.
The property is unaltered if you add or multiply. Multiply with non-zero constant. Okay. Now we prove that all the 11 integers have the same parity. That is, all are even or all are odd. How do you prove if either all are even or all are? Say all the given integers, either all are odd or all are even. How do you prove that?
So because the total sum is equal to, means the sum minus any number is always even.
Exactly.
The net sum of 11 numbers.
Exactly. So if you look at the S, if you look at S as their sum, if S is their sum, then S minus 7. See, if you delete one integer, the remaining 10 integers can be divided into 2 equal parts. Therefore, s minus a1 will be even. Similarly, s minus a2 will be even, s minus a11 will be even. Therefore, these numbers will have the same parity as, therefore all the 11 numbers will have the same parity. Therefore, a1, a2, a3 will have the same parity as s. Okay. Now, you subtract a1 from each of the integers, then those 11 numbers, if you subtract a1 from a1, you will get 0. Then a2 minus 7, a3 minus 7, etc. will have the property p, because you can add any real number. Okay. But then these are integers having the same property p. Since 0 is even, all the other integers also will be even. Therefore, you can divide by 2 and still get integers. So that's what I'm going to do. I divide by 2, you get 0, a2 minus a1 by 2, a2 minus a3 minus a1 by 2, a11 minus a1 by 2. They have the same property p. But again, one of them is 0, and these are all integers. Therefore, again, all these will be even because 0 is even. Therefore, I can divide by another 2. So I get 0 by 2, 0, a2 minus a1 by 2 squared, a3 minus a1 by 2 squared, a11 minus a1 by 2 squared. They're also integers having the property p. Again, 0 is even. Therefore, these numbers will be even. Therefore, I can divide by another 2 and so on. So I can divide by any power of 2 and still have integers. So, for example, if you look at a2 minus a1 by 2 power k, a2 minus a1 is divisible by 2 power k for any integer k. So, what does it mean?
It should be 0.
It is equal to 1.
Because as soon as it's a non-zero number, then you can't go on dividing by powers of 2. Okay, so it should be 0. Similarly, this should be 0. So all these numbers should be 0. That means a2 minus a1 is 0, a3 minus 7 is 0, etc. Which means that all the numbers are equal to a1, which means a1 equals a2 equals a3 equals, etc. Okay. So we have proved it for not just integers, for negative integers also, for integers in general, because we didn't assume that a1, a2, etc. are just positive integers. They can be any 11 integers. Okay. Having done this, just a few comments. It is easy to see that even if a1, a2, etc., a11 are rational numbers, the result can be proved. How do you prove for rational numbers?
Sir, we will take the LCM of Q1, Q2 up to Q11 and multiply it by the whole.
Exactly.
Let's multiply all the numbers by that.
Exactly. So this take the LCM of the denominators, multiply all the numbers. The property P is still true. Therefore, all the multiplied numbers are equal. Therefore, those numbers will be equal. In fact, you can prove it for real numbers also. But here you can't take LCM of denominators. The proof will require linear algebra as a branch of mathematics.
Sir, we can do it by continuity of number means.
Well, I don't think you can give a neat proof with continuity. Okay. Once you prove it for result for real numbers, you can prove that for complex numbers is very easy. So once if you prove for real numbers, complex numbers won't be a problem. You can try to prove this also.
Sir, we will separate the complex into the real and imaginary.
Exactly, and the property will hold. That exactly that's the proof. Okay. I'm not. I'm going to stop here. See. What about multiplication? See here, you can split into 5 equal parts with equal sums. But what about products? Think of what can be done with products. For example, product of 5 integers equals product of 5 integers. Will the result be still true?
Sir, I think no.
No, sir.
Yeah, because what's the reason?
Sir, 2 numbers could be taken 0. I mean 3 numbers.
Yes.
Take 3 numbers 0 and we are done.
Yes, you are right. So if one number is 0, anyway, equality is not possible. If even if 2 numbers are 0, equality is not possible. But if 3 numbers are 0 and the remaining 8 numbers are arbitrary, then equality is possible. Therefore, the conclusion was true. Now suppose no number is 0. Now suppose no number is 0. Then the conclusion will be true. If no number is 0, you have to prove that all the numbers are either positive or all the numbers are negative. So you can easily make all the numbers positive by multiplying minus sign. So all the numbers can be made positive. Now, if you take logarithms, multiplication becomes addition. So using the previous case, you can prove that all the numbers are equal. So even for multiplication, it should be true, provided no number is 0. You get the idea? Multiplication can be changed into addition by taking logarithms.
Yes, sir.
Okay, that's the idea. That's the main idea. Okay, I think the time is over. So thank you very much for giving me this time. I would like to thank Sumana. Are you there?
So,
anybody from
yes,
HBCSE?
sir, can you share your email with?
Sorry. Yeah,
Sir,
all these solutions will be sent to you.
Sir, I mean, can you share your email with us so that if we have any doubt, we can ask regarding higher mathematics.
Sir, they will be sent to you by HBCSE, by email.
Okay, sir.
Okay, no, was that your question?
No, sir, I was asking about that if you could provide your email. That's
My
that's
email.
it.
Yeah,
Yes,
yeah, I can. It's well, I don't know if it is already provided to. My email is prawn, PRAN.
So can you write it, please?
Well, I need to adjust the camera, etc., etc.
Sir, on screen, just write it. We'll look.
On screen. Okay.
I'll see.
Okay, sir, we can stop here. Sumana ma'am is not there, so.
Yeah, sure. So I'll just write my email. You can note it down. So prawn, PRAN, at alumni dot IISC dot AC dot in.
Thank you, sir.
You got it? Prawn at alumni dot IISC dot AC dot in. Okay. So thank you very much. Yes.
Dot IISC dot
AC for academic. Dot in.
Sir, what's that prawn and then that E symbol at the rate?
No, that is at the rate. So I wrote it quickly. It doesn't. It looks like E. So it is at the rate.
Thank you, sir.
Okay. Right.
Thank you, sir.
Right.
Thank you, sir.
You're most welcome.
Thank you, sir.
And all the best to you.
Thank you, sir.
Thank you,
Right.
sir.
Thank you, sir.
Thank you, sir.
Anil sir, we can stop here.
Yeah. Who is this place from HBCSE?
Gaurav, I'm Gaurav, sir.
Oh, okay, okay. Say, how many attended this program?
Around 128 students were there.
120 students.
128 around.
Yesterday, in the same session, how many were there approximately?
Around 94, 95 students.
So
in between.
Normally, that is the number. Okay.
Yes.
So that many have been selected, a kind of around that number.
Actually, more have been selected, but due to there's exams going on and some other personal issues, students have not attended.
Classes, yeah. Actually, the number should be like 300 to 400, no?
Exactly. 380 around we're supposed to attend, but more.
Okay. Anyway, thank you very much, Gaurav. Okay.
Yeah.
Convey my regards
Thank you,
to
sir.
Sumana. Okay, thank you. Disengage.
Thank you.
Thank you.
Thank you, sir.
Okay.
Thank you, sir.